Christopher Nolan's Interstellar introduces the audience to various aspects of space and time, both real and fictitious. One of the topics referenced continually throughout Interstellar is time dilation through the effects of gravity. There are two ways of thinking about this dilation, the one originally conceived by Einstein and one that is a little simpler. Einstein originally postulated in his theory of special relativity that when objects move faster, time slows down more for them. Einstein theorized that through considering terminal velocity, it can be seen that an object experiencing a greater force of gravity will move more quickly, and thus time will move more slowly for the object via special relativity. Another way of viewing this problem is through the consideration of gravity bending space-time, as has been measured by none other than Kip Thorne, who won a Nobel Prize for his contributions. This theory is that massive objects will bend the fabric of space-time, and thus create longer paths for objects to travel in the fabric of space-time. We all know that velocity equals distance over time, and that the speed of light is constant. So when light has to travel farther in the same amount of time at a constant speed, the only possibility is that time itself must slow down. Interstellar poses this phenomena during the second act of the movie, when the crew of the Endurance must take a detour to explore Miller's planet after a rescue beacon is set off. The catch, thanks to the extreme gravity exerted by the planet by its proximity to a black hole by the name of Gargantua, which is the center of the system. 1 hour on Miller's planet is equivalent to 7 years in Earth time. But with this information and research from Kip Thorne's contribution to physics, a new question can be posed. Is the time dilation on Miller's planet an accurate equivalent given the limited information given about Miller's planet, Gargantua, and the solar system itself?
To most accurately put this to the test, we took the given information about the system and applied them to real-world physics. Using constants and equations found online, we first found information about both Gargantua and Miller's planet, although we did have to improvise with unavailable information such as the mass and radius of Miller's planet, which we substituted with information about Earth. To find the gravitational time dilation on Miller's planet, we found the following equation, with Tr being the elapsed time inside the gravitational field, T being the elapsed time outside the gravitational field, R being the distance from the center of mass of the planet to the black hole's Schwarzschild radius, also known as the event horizon, and Rs being the Schwarzschild radius. Then we went about finding the required variables to solve for Tr when T is equal to 1. To find R, we learned that the tidal radius or Roche limit of the planet is equivalent to the distance from the center of the planet to the closest point where a planet can be where it is not distorted by the black hole's gravitational field. We found that the tidal radius is 29,747,166,768 meters.
Next, we had to find the Schwarzschild radius of Gargantua. The Schwarzschild radius is the radius of the event horizon, where nothing, including light, can escape. To find Rs, we used the Schwarzschild radius equation and found it to be 296,855,034,955 meters. Now, we were able to solve the equation of gravitational time dilation on Miller's planet caused by Gargantua and intergravitational pulls. Using the information we calculated and found through research, we found the time ratio on Miller's planet to be 1 to 0.0455292. With this calculation, we are given that for every hour on Miller's planet, about 21.96 hours pass on Earth, or 21 hours, 57 minutes, 50.05 seconds of time. Maximum.
With this data, we conclude that time dilation on Miller's planet was a significant overestimate to better serve the plot.